Okay, so the next recursive function that I want to work on is a function that is going to find the smallest item in an array. Not very exciting, I know, we've already done that using iteration, right? But we're just going to use it as another simple example and see how it goes trying to use recursion to solve that same problem. Okay, so here's my header for the function. Going to have a list of numbers, and I need to know how many items there are in the list. Okay. So, base case. What's a case in which we can instantly just return the correct answer? If there's only one item in the list, right? And so how do we test that? If num items equals 1. Okay, so there's our base case. Whenever you write a base case, you should probably just stop for a second and think about whether there is an even simpler base case. Is there a simpler base case in this situation? Okay, so what about if the list is empty? If num items equals 0, then what are we going to return? If there's no items in the array, then the smallest item in the list is 0. Okay, so I think the correct way of looking at that is this function shouldn't be called if there's no items in the array, right? So we probably need to make that a precondition. Num items is greater than 0. So maybe we could even assert that. Okay. So yeah, I think that's good for our base case. If num items is equal to 1, what do we want to do? Right? That makes sense to everyone? Okay. Now we get to think about the recursive case. Maybe how should someone tell me what one thing that we can say for sure is going to be in this next section? No, I think that you're right that there will be an if statement in there. I guess I was thinking a little bit further ahead than what I was. I was thinking like just very rudimentary without even thinking about the algorithm here. What do you know is going to have to be there? Okay, right. This is a recursive function, so I'm going to have a call to find smallest in there somewhere, right? So I'm going to just throw that in there for now. And I guess the other thing I would say is there's going to be a return, right? So it's going to be something like and then what are the arguments going to be when we make this recursive call? So notice what I'm doing here. I'm not even thinking about how this is going to work yet, right? I'm just kind of trying to put some pieces in there. And I don't know, maybe that's not always the best approach. Maybe it might be better to try to think about the big picture first. But I guess the reason I'm doing it this way is to just kind of show you that if you can't see the big picture right away, sometimes you can get there by just starting to put pieces together. Okay, I'm going to send a list. And it makes sense that I would send num items -1, right? Because you have to get closer to your base case, right? And again, it's not always going to be -1, but that's a pretty good place to start. I mean, it might be divided by 2 sometimes or something like that. But -1 is a pretty good guess at it. And if you think about it, it sort of makes sense that if we can find the smallest item in a list with num items -1 in it, that will help us find the smallest item in our whole list, right? So what does this give us? So here's the next step. We've got our recursive function call down. Now we need to think about, okay, what does this give us? In terms of, yeah, can you articulate that? I guess not.
It's going to return smallest item
Okay, it's going to return the smallest item in a list, one smaller than list. That's correct. I guess I would change the article there. It's going to, instead of saying a list, it's not just any list, it's this particular list, right? It's going to return the smallest item in the list that's one smaller than this list. Okay, but can we be more precise about in what way it's one smaller? It's not just any list that's one smaller. It's not like the whole list except for the fourth element, right?
The last index is more.
Right. This just gives us the smallest number in the entire array except for the last item. It's not going to look at the last item. Does that make sense? That's what this function call is going to do. Okay. So again, I don't know if you. I'm doing a lot of what's the word? Instruction, I suppose, about sort of the process you need to go through when you write a recursive function, but I'm sort of not spelling it out formally. I'm kind of showing it. So just kind of, if you either take notes in your brain or on a piece of paper or something about sort of the process we're doing here. One of the things you have to do is you have to think very precisely about what that recursive function call is going to get you. Okay. So now that we have a way of finding out the smallest item out of the entire list, not counting the last item, how are we going to find the smallest item in the whole list? Yeah.
Well, I think one of the next steps would be to shuffle the last two indexes on the list that the first are making. So that if compare the last two, compare num items, list of num items, and list of num items minus one, and set list sub num items minus one equal to the rest of those two.
So that you throw the biggest number out. Right. That's not, but I'm trying to think, would that work? Would it work to just look at, he's suggesting just look at the last two elements and move the biggest one into the of those two to the last position and then do our recursive call. I think that might work. I think there's a simpler way to do it without having. Oh, well, the other problem with that is that we're changing the array, right? So this probably should be const here, right? Because this function isn't intended to change the array. So think about it. We can find the smallest item in we've got a list, and we can find the smallest item out of the first n minus 1 items in the list. How are we going to find the smallest item in the whole list?
Just go through and compare each number to the other. Do you keep count, or you?
Well, so I think
index numbers when the smallest when you compare it to the other numbers.
So I think what you're describing is basically an iterative way of doing this, right? So we're going to do this. We could do it that way, but we're going to try to do it without having to actually go through the array, like with a for loop or something. So so we've got this last number in the array, and then we know what the smallest number is out of the n minus 1 items in the array. What if we compare those two things? Compare the last item in the array with the smallest item out of all of the other elements in the array. And the smallest between those two will be the smallest item in the array, right? Should I say that again? No, okay. So Sergi's online. I guess you guys can't see that, huh? And he typed in the correct answer, and I didn't notice until after I had told you. So if list sub num items minus 1, no, yeah, minus 1, because that's the last item in the array, right? If that's less than the smallest item out of all the other items in the list, then return list of num items minus 1. Oops. Else actually it's this, I think, huh?
Should there be a comma between the RDLS and false between the list?
Oh yes, thank you. Does that make sense to everyone? Okay, so let's okay, so this is a case where, oh, you know what? I should write this differently. No, it's just what I just did. When we have a sequence of else-ifs, we don't usually like nest them like I had them before. We just kind of sort of make them all at the same level so that there's obviously 3 branches here.
So it's like one of the square brackets is right here. You still do the hit. Possibly using else here, right?
Okay, so let's go ahead and test this out. So we could say int mylist 100, and then we can initialize it to just some random numbers, 4, 6, 2, 9, 5, 1, 7, 3.
You still need to go to the prototype for
Yes, I do. And then we're going to just say int. I'm going to do that. See how the smallest item in the list is find smallest list, comma 8. Yes. And we also need to const into CS. Ready? Oh wait.
It's not like in the brackets. I think there's one out of place, or there should be one more somewhere.
Oh, I'm missing a paren right here. Okay. All right, let's take a look at our code now, because I think we could make a couple of improvements. Anybody want to take a shot at what I'm seeing in here that I don't like? Yeah.
You're calling find smallest potentially twice.
I'm calling find smallest potentially twice, right? And in fact, usually twice.
Yeah.
And with recursive functions, that's particularly a problem because each time you call it, there's likely to be a series of additional function calls, and those are fairly expensive in terms of like efficiency and things like that. So we should probably try to avoid that. So what we could do is just set it to a local variable first, and so we only have to call it one time, right? So we could do something like, go back to the way I had it before. So int smallest okay, and then we're going to say if less than smallest. My brain's just like take a break there. Else return smallest. Boy, I've got that all messed up. Does that look right? Should we try it? Good? Okay. I'm going to suggest, whoops, one more way that we could make this even simpler. Basically, really what we're saying here in this whole else part is return the smallest between these two numbers, right? Between these two expressions. So if I had a function that just returned the smallest of its two arguments, I could just call that function, right? So instead of all of that down there, I could just say return min of lists of num items minus 1 and find smallest list of items. That make sense? And then getting rid of all of that. And it turns out that C++ actually has a function named min that we can just call. So that actually makes it look pretty nice, I think. Yeah?
Looks a lot neater now.
Yeah, so now we've got, I'm not counting the assert, we've got what, a 4-line function there. Okay? Any questions about this example? All right, I'm trying to decide whether I should take a few minutes. I think it'll be pretty quick. Let's see how if we might analyze this function. For example, if we were just looking at it for the first time and trying to figure out what it did. So paint. Okay, so this is our function call, and this is our intermediate result, and this is our final result, right? So let's say the function, now we're going to have to be a little bit clever here about how we represent this, right? Somehow we're going to have to actually represent the array here in our diagram, in our table. So let's say the function call is, I'm going to abbreviate and just say find smallest. And let's say the array is 4, 6, 2, 2, 9. So that's how I'm going to just my own notation that I just kind of made up so that I can keep track of it. Okay, I'm not going to use an array with 4 items in it, and then num items is 4. Right? Okay, so if I call my function with find smallest with these arguments, what's going to happen? Num items is not 1, so I'm going to do the recursive case, min of min of list of num items minus 1, which is what? 9. That makes sense to everyone? Okay. And find smallest 4, 6, 2. I guess actually that's not going to change, huh? What's going to change is num items. That make sense? The intermediate result is the minimum of 9 and the result of this function call here. So I'm actually missing a closed paren. Any questions? Okay, so I'm not ready to get my final result yet. I need to figure out what this function call, the find smallest function call here returns. So I'm going to go over here and I say, okay, now I need to know find smallest 4, 6, 2, 9, 3. Right? And that's going to, my intermediate result there is going to be the minimum of what? 2, and find smallest, same thing. 4, 6, 2, 9, 2. Bummer. Make sense? Okay. I can't figure out that solution, final result yet. I first have to figure out find smallest of that comma 1. So I come over here and I say, okay, I need to know what find smallest of 4, 6, 2, 9, 2 is. Well, that's going to be the minimum of 6 and find smallest 1. Okay, and so that means I need to figure out what find smallest 4, 6, 2, 9, and 1 is, and that is what? So It's 4, right? Because num items is 1, that means I'm really only looking at the first element in the list. Does that make sense? So when I'm doing all these function calls, I'm writing the whole list still, but really another way I could have done it is I could have just written down the part of the list that we were talking about, right? So this is the second time here when I call find smallest of these 4 items in the array and num items equal to 3, that means I am not even looking at the 9. I'm just looking at the list 4, 6, 2, right? And here when num items is 2, I'm just looking at the list as it included 4 and 6, and that was it, and so on. Okay, so the answer here is just 4, right? Okay, so I'll go ahead and put the final result down there, 4. Now I can start going back up. The minimum of 6 and this function call, well, this function call turned out to be 4, right? So min of 6 and 4 is 4. Keep working my way back up. Now I know that find smallest here with num items equal to 2 has a result of 4. So now I've got to figure out the minimum of 2 and 4. Did I mess that one up? Oh, no, that's right, okay. And that is 2, right? Okay. So now I know that find smallest of the list with num items equal to 3 gives us the result 2. So I can plug that in up here, and I'm finding the min of 9 and 2, which is 2. So that's my final result.
Okay.
Any questions about that?
Okay, this makes sense.
Okay. All right, let's try something else. Let me go ahead and get rid of that. Okay. So what I'm going to do on this one that's a little different is instead of, so far both recursive functions that we wrote were value returning functions. So I wanted to do an example of a recursive function that actually was a void function and produced some output. Okay, and this is actually taken straight from the text. We're going to do write a function that takes an int as a parameter and prints that integer vertically instead of horizontally. So if the integer is 47,962, it's going to put 4, and then below the 4 will be a 7, and then below the 7 will be a 9, and below the 9 will be a 6, and so on. Okay? All right. So I don't know about you guys, but I kind of like recursion. It kind of makes me feel a little bit like it's a little bit like a puzzle you're trying to solve, right? You're trying to fit the pieces in and make it work. So this is going to be right vertical. So it might be an interesting exercise to think at some point about how you would write this iteratively, right? It can be done, obviously, but it's actually a lot harder, I think, than writing it recursively. So, all right, int num. So, what is our base case going to be? If num is less than 10? Right, because that means if num is less than 10, there's only one digit, and we just write it out. So, see how, if num is less than 10, And so I guess we're, once again, assuming that num is greater than, I guess it could be 0, right? Yeah, it could be 0. Greater than or equal to 0. Okay, if num is less than 10, we just see out num and del. Okay. So that's our base case. Okay, recursive case. We know we're going to call right vertical. So let's just get that down. Right vertical. Okay, so we have this function that can take any number and write it vertically. How are we going to use this function to accomplish our task? Just thinking, not C++ right now, but thinking algorithmically. What's the strategy going to be? If I said, so the answer that we need to give here is going to be something in terms of right vertical, right? It's going to have to be something that has to do with calling the right vertical function. Hold on just a sec. So here's another way of thinking about it, okay? Pretend that C++ has a built-in function named right vertical. And you can call it to get this job done, right? The only condition is you can't call it with just the exact same number. You have to call it with something that gets you closer. You have to call it with a smaller number, right? So, go ahead.
You're going to divide by 10.
I'm going to divide by 10.
Just like moving through the array to the left. You're going to divide by 10 and start moving through the numbers to the left.
Okay. The way I would say that is we have a function that writes a number vertically. Let's use that function to write the first 3 digits of that number vertical. Not 3. The first n-1 digits of that number vertically. And then we can just print out the last digit by ourselves. Does that make sense? So what I'm saying is, ignore that one. Write the first n-1 digits vertically, right? And we can do that by calling the right vertical function. And then write the last digit. And then we'll be done, right? Okay. So how are we going to do that? Write the first n-1 digits vertically instead of doing it on top. I'll do it here. So we're going to call right vertical, and the argument will be num divided by 10, right? Because that basically just gives us the first n-1 digits of the number. Okay, so we got that done. Actually, I might just leave these up here. Okay, so now we have to write the last digit. How are we going to do that?
See how it's moving.
What do you think? So try it. Oops. Say again? Oh. Prototype. That's what it was. So it's 47,962. Good? Okay. If I were to analyze this, I've already got my table here, so I'm just going to continue on down below. And so, you know, I'm not analyzing these things by showing you the stack growing and shrinking. I did that on our first example, and it might not be a bad idea, but I'm just thinking might just be too over the top, like tedious. So I'm going to pass on it unless you guys, you know, really think I should do it. So the function call, the original function call would be right vertical, let's do like 476, well, or 276. Okay, so the intermediate result would be, now how would we represent this? Well, we might have to be a little clever. Let's pretend this is our screen, and it would be, we first print the result of right vertical 27, and then right below that we write a 6. Okay, can't do our final result yet. Okay, now you see here, this is just kind of a made-up notation that I'm using as a way, in my mind, to represent what's going on here. Right? There's nothing formal about this at all. So we need to know what the result of right vertical 27 is going to be. Well, that's going to be right vertical of 2, and then underneath that we're going to write 7. Okay, so that means we need to know what the result of right vertical 2 is, and we know that the result of right vertical 2 is 2. Right? So now we can do the final result, just 2. Okay. Now we can move up, and we see that the result of calling right vertical 2 is just this down here in the corner. So I replace that function call with its result. So 2, 7. Okay. Now I can go back up here. I know that the result of calling right vertical 2, 7 results in this output. So I'm going to do 2, 7, and then under that goes 6. Okay? All right. That was quick. We're getting good at this. I am going to. I have one more example on recursion that I want to show you, and we'll see how far we get on it. It's a little bit more complex than the ones we've been doing. So, let me just get set up here. So I have to tell you a story off for this one, okay? Has anyone heard of the Towers of Hanoi? Yeah? Where did you hear? What's that? Math 4. Really? Is that where you
Right in the context of program.
Right, okay. So, in the mountains near the city of Hanoi, there's a Buddhist monastery. Outside the monastery, there are 3 tall towers, which we will call left, middle, and right. And okay, and 64 stone discs. Each of the discs has a hole in its center so that it can be placed on one of the towers. So think of the towers as poles that the discs go on. Each disc is a different size. At the beginning of time, all 64 discs were stacked on the left tower, ordered from largest on the bottom to smallest at the top. Day and night, the monks who live in the monastery unceasingly move discs one at a time from one tower to another. They never place a disc on a tower that holds a smaller disc. So that's like a invariant, right? The invariant is that the discs on every pole are always ordered from smallest at top to largest on the bottom. When they have moved all 64 discs from the left tower to the right tower, it will be the end of time. Okay, so we're going to try to write a little program to simulate that and try to figure out how much longer we have before the end of time. What's that? Tomorrow? Yeah. November 22nd, 2012. Okay, so I'm umming a lot here because there's a website that I wanted to show you, and hold on a sec. I think I can do this. We will. Don't worry. Give me a second here. I can find it. That's Thanksgiving. You. Shoot. Oh, come on. Okay, I think I got it. Okay, here's my, oops. Here's my Towers of Hanoi website, and I'll post a link to it. But before we can actually solve this problem, we need to kind of play around with this a little bit, right? So we sort of know what the strategy is. So you guys want to help me figure out how to get these 4 discs from left to right? Go ahead.
Okay, so first move the top one.
To the middle? Okay.
You have to move down all the way to the right.
Okay.
I'll put the middle one around.
Okay.
Now the left one is the middle. Now the right one, I'll go back to the left. Now the right one is the middle. And then,
I think you got it, huh? Okay, so what percent of the way done are we now?
yeah, 'cause maybe,
Don't give me an exact number, but roughly speaking, what percentage of the way done are we? Half and half? Less than half? Well, tell me what we accomplished so far. Actually, let me move this back for a sec. Tell me what we've accomplished so far. No, just don't think about C++ for a second, okay? Don't think about C++ or programming for a second. Just look at the picture and tell me what we've accomplished so far. We moved everything but the last one from left to middle. Okay. What do we have left to do? 2 steps.
We gotta make sure we put the largest block on the.
Okay, so step 1 is put the largest block to the right. And then step 2 is
Move them all back.
move 3 blocks from the middle to the right.
Reverse everything we just did.
Just the same thing we just did, except different towers, right? So put this all the way over. Now we have to get these 3 over here, right? So tell me what to do.
Put the small stone over to the right.
Right? Okay. This one?
And then you move the small stone over to the right. You put the ring on the right. Back to the middle.
Yeah. Okay. So, I just want to make an observation. I don't know if you guys thought hard about which pole to move the first one to or not. What I'm guessing is that you made a lucky guess both of those times, because if you move the first one, so going back to the beginning. If we move this, we have 2 choices about where to move this first pole to, first block. Is that what you call them, blocks? Discs. So we have 2 choices where to move the first disc to, right? And it turns out that it matters. If we move it to the wrong one, then we'll get stuck. Okay, so we got to figure that out too. Okay, so I think, does that give you enough of an idea? Does that, hopefully at this point you're already sort of thinking, I kind of know how we're going to do this using recursion. Okay? Because when we talked about what we need to do here, basically what we need to do is move n-1 disks from left to middle, then move 1 disk from left to right, and then move n-1 disks from middle to right. Okay? So, just to keep things simple, we're not going to actually write the graphics to solve the Tower of Hanoi problem. We're just going to make it print out a list of steps. Okay? So each step is going to be move a disk from blank to blank. Move a disk from blank to blank. Move a disk from blank to blank, and so on. Okay? So in this case, it would be move a disk from left to middle. Right? Is that what we did? Right. Okay. So, and like I said, that matters. So move a disk. So our output when we execute our program is going to say move a disk from left to right. Move a disk from left to middle. Move a disk from right to middle. Move a disk from left to right. Move a disk from middle to left. Move a disk from middle to right. Anybody getting uncomfortable here? Move a disk from left to right. We have a problem, I think, right?
Yes.
I think we're stuck. So we moved the first disk to the wrong place. Okay. As it turns out, that's useful information for if you're trying to impress your friends by solving the problem, but it actually doesn't even come into play when we're writing our recursive solution. Okay? So, shall we take a look at our code for this? All right, so I guess this seems like a fairly complicated task, right? When I look at this, I think, okay, this seems like it's going to require a lot of lines of code, right? Because I'm doing a lot of moving around and calculating and trying to figure out what to do. And I'm pretty sure that if you tried to do this iteratively, it would end up being lots of lines of code. But let's see what we can do here with this. So I'm going to write a function called move disks. Okay, and what are the parameters going to be? One of them. Give me at least one.
Well, one of them is going to be the number of the disks.
One of them is going to be the number of the disks. The other thing we need, so remember, this function is going to print instructions like move a disk from blank to blank, right? So the other thing we need to know is what are the 3 poles, right? And we need to keep it general. We don't want to have it be left, middle, and right. So we're going to say, and these are going to be strings, string source, string target, string storage. Does that make sense? So when I call move disks in main, we're going to say move disks 5. The source is going to be left. The target is going to be right. And the storage is going to be middle. That make sense?
I still don't know why we couldn't just use left, right, in the middle. It makes it a lot easier. Here's why. We need to write a move disks function that can move any number of disks from any pole to any other pole. We don't want to write a function that just moves disks from left to right. Okay.
Does that make sense?
Yes. Yeah, then you want to move it to the left. Okay. Okay.
Right. So source could be the middle one, target could be the left one, who knows. Okay. Okay. What's our base case going to be? Num disks equals 1. I think that could be a base case. Is there a simpler base case?
Num disks equals 0, you're done.
If num disks equals 0, you're done, right? You don't do anything. Okay, so we could say if num disks equals 0, do nothing. Else, then our recursive case, right? No, we can that can be our recursive case. So the question was, don't we also have to check if num and do something different if num disks equals 1? The answer is we could do it that way, and actually I suppose it might be slightly more efficient if we did it that way. But because we wouldn't be making a recursive call in that case. But if our objective is to just keep our code as simple as possible, we only need the one base case. We don't need to list all of the base cases. So
I didn't realize that if you wanted to do nothing, you just left the blank bar when you did that.
well, sure. I mean, if there's no statements there, then nothing's going to get executed. But this isn't a good way to write this, right? Let me just, for completeness.
right? And the base case is do nothing. So really, we want to just say if num disks is not equal to 0, do the base case, do the recursive case. Does that make sense? Okay. So that if statement, that if else statement I have there is actually equivalent to that, right? So let me get rid of this. Okay. We already identified that we have 3 steps, right? First step was move n-1 disks from where? From source to storage, right? From whichever pole we're moving things from to the pole that we're using as a temporary holding spot. So move disks n-1 source from source to storage using the target as a storage place, right? Everyone okay with that? Oh, thank you. Okay, the second step was move 1 disk from source to target. Let me just see exactly how I wrote that. Does that look okay? And then the third step was move n-1 disks. Those n-1 disks that we moved to the storage pole, move them from that storage pole to the target pole. And then we'll be using the source pole as a holding spot. Done. Believe me? That's interesting that that's not underlined. Huh.
Sometimes you can give an answer to your file.
Right. Okay, so we try it. 5 disks? No, let's do it with like 3 to start. Yeah, just so we can see if it's actually giving us correct instructions. Okay, move a disk from the left tower to the right tower. Move a disk from the left tower to the middle tower. Move the disk from the right tower back to the middle tower. Can you guys visualize this, or should I?
No, I can visualize it.
Okay. What's that? No, I wasn't going to use paint. I could go back to the website we were doing and do it there, although it would have to be 4. So Anyway, go ahead and read through those, and I think you'll find out that if you follow those steps, you'll successfully move 3 disks from the left tower to the right tower. Okay?
Yeah, that works.
Okay. So, I still need to find out how long I have left before the end of time, right? So let's figure out how long it'll take those monks to move the 64 disks from the left tower to the right tower.
Now, doesn't the binding conversation December 21st?
So let's start by figuring out how many moves it will take.
I just think it'd be funny, no matter what you do, it always is December 21st.
That would be funny.
No matter what you do.
Okay, so I need to use paint just to draw a little table here. Don't save. So I want to figure out how many moves it's going to take. Okay, so this is going to be sort of an algebra type problem. So here I have n, and here I have number of moves. Okay? So the way that I like to figure this kind of thing out is just start with some simple examples, right? And work my way up and see if there's a pattern. So if there's 1 disk, how many moves does it take? 1. If there's 2 disks, how many moves does it take? 1 to move it to the storage. 2, 3, right? Okay. 3 disks, we could go back and look at our output again, but 1, 2, 3, 4, 5, 6, 7. 7 moves. Here's another way of looking at that, right? In order to move 3 disks, what do? We move 2 disks, and then we move 1 disk, and then we move 2 disks again, right? So 3 plus 3 plus 1, 7. Okay, now using that same reasoning, it should be easy for us to figure out how many moves to take 4. 15, right? Because we got to move 3, that's 7 moves. And then we have to move 1, that makes 8. And then we move 3 again, that's 7 more moves. So 15. 7 plus 7 plus 1, 15.
Okay.
5 would be what?
31.
31. Anybody see the pattern here?
Okay. So it would be 2 times n minus 1. Yes.
2 times n minus 1.
Well, the moves that takes n minus 1. Yeah. How do you want to represent that?
Well, I want to know how many moves it's going to take me if there are n disks, right?
The first we know how many moves it takes to do n minus 1 disks.
Well, we can actually, if we see the pattern here, we can actually write an expression, write a function of n that tells us how many moves it's going to be. Let me do one more. 6 is 63. Anybody see anything that all these numbers have in common? All odd? That's true, they're all odd. They are not all prime, right? What if I used these numbers instead? 2, 4, 8, 16, 32, whoops, 32, 64. Oops. Okay, so all I did is I just wrote down one bigger than that number, right? What are those numbers?
2.
Those are powers of 2, right? 2 to the n. So the number of moves is always 2 to the n minus 1. See this in algebra fun? 2 to the n minus 1. Okay, and it kind of makes sense because each time we go, let me not go there. Okay, so back to our problem of figuring out how many moves it's going to take. It's going to be 2 to the 64 minus 1, right? So that turns out to be 1.8 times 10 to the 19. That's how many moves. So how much time is this going to take for the monks to move all of those?
1.8 times 10 to the 19 times however long it takes to move one disk.
This number times however long it takes to move one disk. Let's be generous and say that these monks can move a disk a minute. How's that? So it's that many minutes. Does someone have like a big calculator that could do calculations this big? You can do. You want to just do it for me? And I'll tell. Oh, you want me to do it? Okay. Actually, I'm not very good at these things. Okay, I don't have someone else volunteer.
Hours.
Well, no, so it's this many. We decided it's this many minutes, right?
Mm-hmm.
So let's find out how many hours, right? So put that in and divide by 60. That tells us how many hours.
It'd be 3 times 10 to 17 hours.
Okay, hold on. Okay, don't do any more calculations for a second, okay?
Okay.
I want you guys to make a guess. How long do you think it's going to take them to move those 64 disks?
In what?
Assuming they can move one disk per minute.
In years?
In whatever you want to give it to me in. Yeah, no, you can't get that. That's a good guess. No, so in years, sure, in years. Because we don't really have a larger, I mean, you could do it in centuries, I suppose. But
Over 1 million years.
over 1 million years,
Yeah.
you think?
Yes.
I can see that. I could be over that.
Because it's
Okay.
500,000
So
minutes.
that's 2 votes for over 1 million years.
6. So you don't even take 6 off of that 19 at the most. So we're going to be like trillions.
Anybody else want to take a shot at it? Everyone?
You
You guys think it's going to be more than 1 million or less than? How many people think it's going to be more than 1 million? How many people think it's going to be less than 1 million? How many people aren't voting? Okay. You guys are no fun at all. Okay. So this is how many minutes, right?
Yep.
Okay. So how many hours is it?
It was 3 times 10 to the 17.
Is that right? 3 times 10 to the 17th hours. Okay. Divided by 24.
1.25 times 10 to the 16.
Oh, sorry, that's days, right? And divide by 365.
.42 times 10 to the 13.
So you're around the money about the years.
10 to the 13, that's a 1 with 13 zeros after it. That's more than 1 million, right? Do we have a name for that number? So if it's got 9 zeros after it, it's a billion, right? Billion. So if it's got 12 zeros, it's a trillion. So 10 trillion times this. So that means 34 trillion Years? Okay. So I'm feeling pretty good actually about my prospects here.
That's just one disk a minute.
So just for kicks, let's talk about how long it would take a computer to move the disks. Okay, and sorry, I know that I said I was going to go over the test, but we're on a roll, so let's just keep going. So to give the computer a little advantage, let's take out the cout statement, because the output statement is like 99.99% of the what's taking the time here. So let's take that out. And we'll just say cout done. Okay. Yes, we have to change it 3 to 64. Let me hold on to that for a second. Okay, so what I need to do is figure out how many moves per second the computer can make. Let's try to figure that out, okay? So to do that, let's plug in, let's try 25 and just see what happens, okay? We might have to pick a smaller number, huh?
Let's just wait a little bit.
Is that? Do you think that flashes once a second?
I was going to say, are you counting seconds?
All right. 25 is too big, huh? Let's try 23. And so let me see if we can actually have the computer time this.
No, we just set a timer as soon as it'll... You're going to have to figure out time.
Right. Well, I can say int time gets... Why am I spacing on this? We did this for... but the function call. This is just time. I think we have to send it something. And then we can say time 0 minus t. That's how many seconds it took? Does that look right? Okay. Look, I don't know why I did that. 23 is still too big. Let's give it a minute. So, actually, what this shows me is that the computer I'm using here is really old. Because I think if I were to use a newer computer, it would go a lot faster.
Yeah, mine's done.
All right, let's, well, let me...
When I read 25, it's like a long time.
Well, every time you increase a number by 1,
It doubles the time,
okay,
yeah.
twice as many.
That makes sense.
Whoa. Wait a minute. Wow, even 20? Oh my gosh.
Do 10. Oh,
13 seconds to move 20 disks. Okay, I think we may need that calculator again. Because I want to know how long it takes the computer to do one move. Or maybe, yeah.
You just talk right away, actually. So how many moves is 20?
So let's figure out how many moves the computer does per second, okay? So 2 to the 13 is the number of moves, right?
What about 2 to the
20 minus 1.
Say again?
2 to the 20 minus 1.
Oh, yeah, sorry.
So it's 1.05
Okay,
times 10 to the 6.
that's how many moves. Is that right?
Yeah.
No, that doesn't seem right.
That would be how many moves per second?
Yeah, that's what you want. Isn't it? You want,
Yeah.
you want how many per second to
Divided by how many seconds?
So the computer does 80,000.
Yeah, you're right, okay.
59 moves a second.
Okay, how many, hold on a sec.
8,600.
Say it again.
80,659 moves per second.
Okay, that's a very slow computer. Let's call it 100,000 moves per second, okay? Okay, so then we need to figure out this number right here, 1.8 times 10 to the 19th. Then divide that by 100,000 to figure out how many seconds, right? Okay, so over here is where I'm going to do the computer part. 1.8 times 10 to the 14 seconds. Okay, divide that by 60.
Three times 12.
Divide by 60 again.
5 times
10 to the 10th. That's hours. So divide by 24.
2.08 times 10 to the 9.
That's days. And one more. 360 divided by 365.
5.7 times 10 to the 6. So it's still be 5 million years.
So 5 million years for our computer to solve the problem, right?
Yeah.
And maybe if the computer was 10 times faster than this one, it would be divide that 500,000 years, right? Okay. So part of the point of all of this is to give you an experience with a problem that would take even a computer way too long to solve, right? So you know, in a few applications, worrying about a millisecond here, a millisecond there is important, but in most applications, the algorithm that you use it can make a big difference, a very big difference. So when we start worrying about efficiency is when we get to some algorithms that could potentially take a completely unacceptable amount of time to run. So in the case of towers of Hanoi, that's just inherent in the problem. There's not a faster way to do it. But in some other things that we're going to be talking about in a couple weeks, such as sorting a large list, you can come up with a very intuitive, simple algorithm that would take the computer, years or something to complete. So we have to work at finding clever solutions that will actually complete that task in a reasonable amount of time. Any questions about any of that? So I guess I just want to say a couple more things about this. One of the things that we're supposed to do in data structures and algorithms class is talk about analyzing algorithms for their speed. And when we do that, basically what we do is we identify what category of function the algorithm fits into. So if you remember algebra, you have linear functions, you have quadratic functions, you have logarithmic functions, you have exponential functions, right? So which type of function is this? The towers of Hanoi is an example of an exponential function, right? So in computer science, when we talk about that, we use something called big O notation. So we would say this is big O of 2 to the n, because that 2 to the n is how we represent a logarithmic function, right? Exponential, thank you. So other options are, we might have, for example, if we have a function that goes through an entire array trying to figure out what the smallest item in the array is, that would be a linear function, right? It's going to, if there are n items in the array, it's going to take n steps to do it. So for that, we would write big O of n. Okay? As it turns out, when we start talking about sorting, the simple sorting algorithms that we start with that are sort of intuitive are going to turn out to be n squared, which turns out to be really bad if we've got like a million things in our array, right? That's probably going to give us an unacceptable runtime for sorting an array. But if we're clever, and we will be, we'll talk about algorithms that will allow us to do this in order n times log of n, which turns out to be much, much faster. Okay, so that's just kind of a sneak preview of what we're going to be talking about when we get to sorting and searching. Not that only sorting and searching algorithms can be analyzed like this, but that's the ones we'll be talking about. Okay, I'm going to stop recording now.